Hi everyone, welcome to week 8. We're going to continue with our application of integration methods that we've learned so far. This week's goal is to learn how to find volumes of solids. Next week we're going to learn another method of finding volumes. So we're going to spend 2 weeks on the volume topic. Finding volumes of solids is an age-old problem. It has immediate applications to a bunch of fields. Well, any field that works with a three-dimensional object requires you to know how to find its volume. There are formulas for some general shapes, but two questions. A, where did those formulas come from? There are geometric ways of getting those formulas. There's also a calculus way of getting the formula. And secondly, how to find the volume of a more general shape. So our goal is to first understand what volume means, and then we find a way to approximate it effectively, just as we did with areas. Now, basic definition is that for a box of side length 1 unit, the volume is 1 unit cubed. So, for example, if the length, width, and height of the box are 1 unit each, the volume is 1 times 1 times 1, which becomes 1 cubed unit. Another way to interpret this is that the area of the bottom face is 1 unit squared and the height is 1 unit. Or we can understand volume as the area of the base times the height. In general, if we have a column of any arbitrary shape but has a perpendicular height of h, then the volume can be found by finding the area of this base times the height. Now you can pause the video here for a concept check. Using this, what is the volume of a cylinder whose height is h and radius is r? Using the idea that the volume is given by area of base times the height. Okay, the solution is, well, the base of a cylinder is a circle, and the area of a circle is pi r squared. So the volume of the cylinder becomes the area of the base, which is pi r squared, times the height. So you get pi r squared h. Now recall that when we approximated areas, we sliced objects into rectangles and we added up the areas, and that was called the Riemann sum, and it came out to be equal to the integration or antiderivative. For volumes, we're going to slice them into cylinders and add up the volumes because the volume of a cylinder is easy to find. One way to visualize how this happens is think of slicing a loaf of bread. Now, if this particular object is sliced here, the cross section may look something like this. Now, using the same trick as with area, we make two slices, one next to each other. Now, when we do this, we have this, let's say the width of the slice is delta x, is really small. Yeah. What we end up is we can say that roughly the top and the bottom are roughly the same because delta x is really small. Right? In fact, that becomes the height of the cylinder. And then we can sort of approximately say that this shape on the top is like a cylinder, or if we can find the area of the shaded region, then we can find the volume of this entire block. And because in general, volume is area of base times the height. And we add up all these volumes to get the total volume. Now when we say add up all these volumes, that process is the process of integration. So let's formalize this method. Let's say we find an expression for the area of the cross section, and we call it ax at some point xi. Then we make slices of width or cylinders of height delta x. Then the volume is the sum of all of these slices. So it's axi delta x summation 1 to n. And this approximation gets better as n goes to infinity, meaning as n goes to infinity, delta x goes to 0. So these are really small slices. So the volume becomes the limit of the sum, which becomes the integral of this area, with the solid line between x equals a and x equals b. The cross-sectional area in the plane through x is perpendicular to the x-axis, and is equal to a of x. A has to be a continuous function. Typically, so caution here, this cross section changes with x. That's why it's a of x, yeah, it's a function of x. So something like this here, if this is the shape, if you take a cross section at x1, x2, and x3, then these have, all three of them have different areas. In fact, this cross section is going to vary continuously, right? Even the one right next to it is not going to be the same. So this varies continuously. And that is why we need a of x to be a continuous function. Okay, stop this video here.